Okay, we'll look at one more example of another asymmetric alkene. This time, well, what have we got here? We have got but-2-ene, 2-methyl but-2-ene. Yeah. It can't exist as, by the way, it can't exist as EZ isomers, can it? Because look, it's got one CH3 and a CH3 group, two groups, both the same there on that carbon. So it wouldn't exist as that's besides the point, really. Okay, let's see how that's going to react with HBr then. Okay, so here's HBr. The first step in the mechanism, pi bond onto the hydrogen, because that's delta positive, that's the electrophile, and then that bond breaks, both electrons go into the bromine. So I'll do it in two different colors. Let's say, right, so let's say that this one, the hydrogen sticks onto this carbon here. All right, so that means that the other carbon is going to be the carbocation. That's the positively charged carbon, okay? And or alternatively, what could happen is you could have the hydrogen sticking on the other one. I'll do that in another color so it looks nicer. CH3, CH3. Right, that's going to be the positively charged carbon because this time that green hydrogen from the HBr is sticking onto that carbon. Okay, so let's see what the product's going to be then. So this one, here's our Br minus. Final step, that's going to attack there. So we're going to get CH3. And we've got our bromine on this one, okay, and the hydrogen there. Let's draw this one, the blue one. That's a 3 knot. It's a bit messy. Start again. CH3. We're going to get the bromine on that one, aren't we? Okay, that's going to be like that. So that's going to be 2-bromo, 2-methyl butane, and that's going to be, well, I should call it 2-bromo, 3-methyl butane, because bromo gets the lowest number because it's a functional group. So let's see, what kind of a carbocation is this one? Let's talk about this one here. What kind of a carbocation is it? Well, it is a secondary, yeah. It's got two other carbons attached, that one and that one. Don't forget, each of those carbons is going to be pushing a bit of negative charge in two alkyl groups into that positive, making it slightly less intense than it would be. But let's have a look at this one. This one is a tertiary carbocation, and that's more stable, isn't it? Because this one has got 3 alkyl groups, all pushing a bit of negative charge into that carbocation, into the positive there, making it slightly less intense. So this is a more stable intermediate. Okay. And that means that this one is the major product. You get more of that, you get less of that. That's the minor product. Now, just a quick word of warning. A sort of classic wrong answer to this is, it will say, why is that one? It will say, why? Let's make this, okay. This up. So I should explain why. So why is that one the minor? And the wrong answer is to say the haloalkane is less stable. Well, it's not less stable than this haloalkane. They've got the same stabilities. The correct answer, what you should say is, the carbocation intermediate that it's formed from is less stable. So, you know, get it right. Don't make that mistake that a lot of people do. It's not these two things that have different stabilities. It's the carbocations which have different stabilities. That is the right answer. The one in blue, not the one in red. Okay, so I think we will leave that there. Just make it smaller so you see it all in one go. And that's the end of that video.